Today we're focusing on projectile motion. Projectile motion is an example of kinematics in 2 dimensions, where in 1 dimension we're experiencing acceleration, specifically the acceleration due to gravity, and the other dimension, specifically the x-axis, or the horizontal component, we're assuming no acceleration. So therefore, in the horizontal axis, we can assume constant motion. In the real world, of course, that is not realistic, because in the real world, we have things such as air resistance, which in fact does not make the x-axis constant motion. And in fact, it does experience accelerated motion, which is entirely dependent on the geometry of the situation, of the projectile itself, the material, its mass, its surface area, its shape, the whole thing. That, of course, makes the questions decidedly more difficult. So like any good physicist, we just choose to ignore those complex parameters. Now, again, this is high school level physics, and those more complex things you tend to deal with in actual practical engineering problems that you would deal with in the advanced years of your university program. So let's talk a few things about what makes projectile motion what it is. So basically, we have 5 rules. For simplicity's sake, as I mentioned, we ignore air resistance, which, of course, in practical terms is nonsensical, but for the purpose of instruction as an introductory course, really, it makes it a little bit easier to tackle on the bigger ideas. The second rule, the vertical component is affected by gravity, specifically the acceleration due to gravity. Now, here's an important distinction. We use the symbol little g to represent the magnitude of the acceleration due to gravity, and that is approximately 9.8 meters per second squared. It's actually closer to 9.81, and that value does actually vary depending on where you are on Earth, but 9.8 meters per second squared is good enough. When we use the parameter little g, we're speaking only about the magnitude of the acceleration due to gravity. That's why there's no negative sign in here. This is just the magnitude. Rule number 3, the motion in the horizontal component experiences no acceleration, so we can treat it as constant motion. The horizontal displacement we refer to as the range, which makes sense because really we're talking about how far along the surface the projectile will land away from its launching point. Just like if you go to a driving range to practice your golf swing, for example. The range is referring to, of course, the distance of your shot. And golf is a pretty good practical example of projectile motion. Rule number 4, this is a very important one. And again, this is assuming no air resistance. And that is the rise time for the projectile is equal to the fall time. So the amount of time it takes to reach its maximum height is equal to the amount of time it takes to come back down to the original launch position. Important thing to note that at the top of the launch, the highest point, the projectile comes to a temporary stop in the y component. So let's say we shot the projectile straight up with no horizontal component of motion. When it reaches its maximum height, it has to temporarily stop and then start to fall again. Okay, so before we get into the mathematics, let's actually take a look at some demonstrations just to sort of reinforce these big ideas. So off to the side here, you're going to notice on the OneNote document, I have this link to this projectile motion demo. And these are produced by a university in the States, Colorado, I believe. And they produce these amazing demonstrations for physics. And this is one of them. So what we're going to do here is I'm actually going to start off with our cannon perfectly straight up. I'm also going to shut off the air resistance on it. And I am also going to include the velocity vectors. Now, the acceleration vector is just the acceleration due to gravity, so that'll be pointing down. But I want to watch what happens to the velocity vectors. Okay, so what we're going to do is we're going to launch our cannonball, and as expected, as it rises, it slows, and then eventually it falls back down again. Let's repeat that, but this time I'll go step by step. So when we launch it, now you can see wherever these markers are, that's an indication of a fixed amount of time. So that is at the 0.1 second mark. Now, as it rises, you can see that the second position at the 0.2 second mark, the distance between the first and the second point is shorter. And that makes sense because we're experiencing negative acceleration. And you'll notice that the green vector here is starting to decrease. So as we increase in height, the magnitude of the velocity is moving towards the negative. And the ground that we cover between each tenth of a second diminishes until we get to approach at least our maximum height. So you can see that the velocity vector up here is very, very short. And then a few more clicks here. And at about that point right there is when we've reached our maximum height. At this point, the velocity of our object must be 0, because when you transition from upward motion to downward motion, you have to temporarily stop. Now, that stopping amount of time is literally just an instant, but it happens nonetheless. So it has to stop. Now, we're of course assuming that there is no x component. And then as time goes on, our projectile starts to fall back down again and then lands back down onto the ground. Okay, awesome. So the next thing I want to demonstrate, let's clear that, is I want to talk about the idea of the rise time equals the fall time. So what I'm going to do is I'm going to launch the cannonball, and then I'm going to launch a second one when our first one reaches its max height. So as we get close in, I'm going to pause it, and then I'm going to increment it until we get to the exact point. And that should be right there. Okay, so now we're at our maximum height. So this should be half the amount of the flight time. So the time to reach max height is half of the total flight time. So I'm going to launch a second cannonball. And what should happen is that the second cannonball should reach the maximum height up here when the first cannonball lands on the ground. All right, so I'll pause it when we get a little closer to the end there. Okay, I'm going to pause it and now incrementally go. And as you can see, we're approaching max height for our second cannonball, and our first cannonball is almost back down on the ground again. And slowly incrementing it, and we're getting very close, and then we should be right there on the ground. And if you look at the bottom cannonball, it stops moving. So that shows you that the rise time is equal to the fall time. So let's prove that mathematically. So here we have a ball shot straight up with an initial velocity of 49 meters per second up. So the first part of the question asks us, how long does it take to reach the top? Okay, so here's what we know. So let's take a look at part A. Now, we know that this is accelerated motion, so here are our following kinematic parameters. We know we have d, v1, v2, acceleration, and time. What we're asked to find in part A is the time. What we don't know is how high it reaches, but we do know the following thing. We know that the v1 was initially 49 meters per second up, or positive 49 meters per second. Now, the key is, at maximum height, when it reaches the top, it temporarily stops. So we know what our V2 is, and that's 0 meters per second. That is an important concept. Whenever you reach the vertex, the highest point on your projectile motion, the y component of the velocity is always 0. And that is when we reach the maximum height, the Vy component is 0. That doesn't mean the Vx component is necessarily 0, but it definitely means that the Vy component is 0 at that point. And of course, the acceleration due to gravity is negative 9.8 meters per second squared. So these are our three known values. We're not looking for displacement. So we are looking for the one formula that has V1, V2, acceleration and time, and that is A is equal to delta V over delta T. Rearranging it, we get delta T is equal to V2 minus V1 over A. Substituting in, we get 0 minus 49 over negative 9.8, sorry. And that gives us a delta T of 5 seconds. So our rise time is 5 seconds. Next, we want to determine how high it rises. Now, when I made this question originally, I used this, the 5 second value, which is not best practices by my own admission. So this is back in the day when I was a little bit more sloppy with my technique. And the reason why is that 5 seconds is technically subject to error. So the formula that would have been best to use, and here's our little list here, we should have used a formula that only involved these parameters here. And that would have given us the best result. So let me just reduce that and get that out of the way here. So the other formula we could have used is this one here, which is V2 squared. Zoom in a little bit there. That would be our V2 squared is equal to V1 squared plus 2AD. Isolating for D, we would get V2 squared minus V1 squared over 2A, which gives us 0 squared minus positive 49 squared over 2 times negative 9.8, which in fact gives us 122.5 meters. Okay, so now let's take a look at the fall time. How long does it take for the fall? So now what we're doing is we're now starting from the very top. So our list is going to be a little bit different now. So when we're at the top of our arc, here's what we know. So we know that since we were at 122.5 meters above the ground, to reach back down to the ground, we have to fall that amount. So that's negative 122.5 meters. Our initial speed, because we're starting from the very top, we're at the vertex, so that's 0 meters per second. Our impact velocity, that is unknown. Our acceleration is negative 9.8 meters per second squared. And the time is ultimately what we're looking for. So of course, that negative 122.5 is subject to error, but by definition, the V1 has to be 0 at that point, and the acceleration is negative 9.8. So we're going to ignore our V2, and we're going to look for the formula that has just dV1 acceleration in time, and that is d is equal to V1t plus 1/2 at squared when we isolate for our time. Now, if you notice, the nice thing about this is that our V1t, that goes to 0. This makes this question much easier to solve. And then you can see that our time is going to be plus or minus 5. So as you can see that the, obviously you can't have negative time. So it's just 5 seconds because time isn't a vector. So the rise time was 5 seconds. The fall time was also 5 seconds. All right, now let's talk about the impact velocity. And the impact velocity means how fast was it moving just as it was about to hit the ground. Now, this is an important distinction because most people think, oh, when it hits the ground, it stops. That's true after you collide with the ground. That's a different problem. We're talking about the speed that it is traveling just at the moment of impact. So it hasn't technically touched the ground yet. We're talking just how quick is it moving, that fraction of a fraction of a fraction of a fraction of a millimeter just above the ground. When it hits the ground and stops, that's a different question. Now, to criticize my own work here, this 5 seconds is actually based on another calculated result. So I'm going to use a darker, dirtier check mark there. And that's to indicate that there's even more potential error here. So I should have avoided using this formula here when I originally did it. But then again, back in the day, I was a little bit more sloppy. So the alternate way we should have done this is we should have worked with these parameters here, d, v1, v2, and acceleration. And that would have meant that we could have used this formula here. V2 squared is equal to v1 squared plus 2 AD. So v2 is equal to the square root, technically plus or minus, v1 plus 2AD equals plus or minus square root of 0 squared plus 2 times negative 9.8 times negative 122.5. And we get plus or minus 49 meters per second. And based on your understanding of what is happening in terms of the actual motion of this object, it is obvious that it's the negative value because it is falling. Okay, so let's focus on another example here. An object is launched horizontally from a height of 490 meters at an initial velocity of 10 meters per second towards the right. All right, so our projectile is launched perfectly horizontally. Assuming no air resistance, we need to find the flight time, the horizontal displacement, and the total displacement. Let's go back to our little projectile motion demo, and let's go to the intro page. So here's a perfect example of this type of question here where the projectile is going to be launched to the right. So when we fire our projectile, you can see that it's making a half parabola here. Okay, now the important thing is to understand is what is happening with the velocities at this point. So let me just turn on our velocity vectors, and I'm going to pause this. Oops, let's try that again. There we go. Okay, so now I have it in pause mode. What you can see here is the green vector represents the velocity at this point. There's only a single component to the velocity. There is no y component of the velocity yet because it's being launched horizontally. Now, as time progresses, you can start to see over here, you can start to see that the y component of the velocity is starting to grow. And that's because acceleration due to gravity. The x component, however, remains unchanged. So as it is flying through the air, you can see that the x component remains the same, but the y component grows. And then eventually we land. This means that if we were to drop a projectile at the exact same time that we fired one, they should both land at the exact same time. So here, let me show you what I mean by this. So I'm going to drop it down to 0. So when I fire this, it's obviously just going to fall straight down. and then let's bring it back up to 15 meters per second. And then when I fire this, it's going to make the arc. My argument is that the amount of time for the first one to hit the ground should be identical to the amount of time that the second one takes. Now, to demonstrate that, I'm going to fire two of them at the same time. One with initial velocity of this 15 and the other one with initial velocity of 0. So let's erase all of this. And then we'll start off. Now, of course, we're all paused here. So I'll fire the first one. And then what I'm going to do is I'm going to drop the speed down to 0. And then I'm going to fire the second one. And then what I'm going to do is I'm going to go step by step. And what you can notice is that the position of the two objects in the vertical, notice that they're at the same height throughout the flight. And they both land at the exact same time. Let's do that again, but this time allowing the demo to actually run its course. So we fire the first one, and I'll have it run slow too. So fire the first one, fire the second one, and now let's start it. And they both land at the exact same time. So that's a key concept, is that at this position here, our Vy at this point is 0 meters per second when the projectile is launched horizontally. Let's go back to our example. Okay, so we know a couple of things here. So first of all, we know that the object is launched horizontally, that's key, from a height of 490 meters. That means that we're above the ground. So let's interpret this in terms of our kinematics parameters and whatnot. So here I have a little setup. So in doing good old GRFS, so our dy, our displacement in the y, and this is important, it's going to be negative 490 meters. And the reason why is because it is falling down. So it's going to move 490 meters down towards the ground. And as I mentioned, the Vy1 is 0 meters per second because there is no y component of the velocity yet. That 10 meters per second is the x-axis velocity. The other thing we know is that the acceleration in the y component is negative 9.8 meters per second squared. And this is absolutely key, that the time in the y-axis is the exact same time it takes to travel along the x-axis because it's the same projectile. So the two times for the ty and the tx are the same time. So we're asked to find the flight time, the range or the displacement in the x, and then the actual total displacement. Okay, well, to find the time, we can either use the x-axis or the y-axis. Well, the problem is this. If we look at the x-axis, we only have one kinematic parameter. We need at least two to be able to solve for the unknown. So we have to look at the y. And if we look at the y component, we have three known parameters. We have the dy, the Vy1, and the acceleration. So we can easily find time by looking for the one formula that does not have Vy2 in it. So Vy2, we don't need. And of course, the only formula that we have that does not have Vy2 is dy is equal to Vy1t plus 1/2 Ayt squared. Now, notice this term cancels out. And the reason why it cancels out is because our Vy1 is 0 meters per second, and anything multiplied by 0 is 0. So our equation then reduces down to dy is equal to positive 1/2 Ayt squared. Rearranging for time, we get time is equal to the square root of 2 dy over ay. Substituting our values in. Now, as you can see, it's very important that you get your negatives and positives right, because if you forget to put the negative on the displacement and you have the negative on the acceleration or vice versa, you're going to attempt to take the square root of a negative number, and you can't do that. So you really have to get your vector directions right. Otherwise, algebra is going to be very angry with you. So that works out to plus or minus 10 seconds. Of course, we can't have negative time, so it's just 10 seconds. Next, we have to find the range or the displacement along the x. Well, now that we know the time of 10 seconds, of course, it's subject to error. So that's why I have the amber check mark. We do now have enough information because we have the known value for our Vx and our calculated value for the time. And that gives us 100 meters. So that's our displacement along the x-axis. It's moved 100 meters to the right along the ground. But the final part is asking for the total displacement. Well, in this case, the total displacement is actually this vector right here. It is not the red dashed pathway here. It's this direct vector here. Let me just highlight it. That would be our displacement. So we have to figure out the magnitude and this angle. Well, since this is a right angle triangle, let's try that again. There we go. Since this is a right angle triangle, we can just simply use Pythagorean theorem, and we can use the primary trig ratios, specifically tan, to figure that out. So substituting our values in, we get approximately 500.1 meters as the magnitude of our displacement, and using the tan function, tan theta is equal to the magnitude of dx, because that's the opposite side, over the magnitude of dy, because that's the adjacent, and we get approximately 11.5 degrees. So the displacement would be 500.1 meters down 11.5 degrees to the right. Next, we're going to take a look at something called the flat ground projectile motion equations. What we mean by a flat ground problem is that the initial launch height and the landing height are the same. So let's label these positions A, B, and C. So in a flat ground situation, the height at position A is 0 meters, and the height at position C is also 0 meters. At position B, that height at position B is known as the max height, or H max. And this point B is actually the vertex, and we have symmetry on the left and right-hand side of this point. The other thing to note, at this position here, the y component of the velocity, or vby, is 0 meters per second. That's because the projectile in the y component has reached its maximum height, which means it's not rising any further, and it's starting to fall at this point. So as far as the y's component is concerned, it temporarily stops rising, nor is it falling for this brief moment. Therefore, it is technically not moving in the y component. Hence, the vby is 0 meters per second. That is always true when we're at the vertex during projectile motion. At the highest point, the y component of the velocity will always be 0. The other important concept, that the time to reach position B we call T max. And this maximum, the time to reach the maximum height, this doesn't mean the maximum time. This means the time to reach the maximum height is equal to 1/2 of the entire flight time, T subscript F, which is the flight time. And again, that's because of symmetry. And it goes back to one of the original concepts, and that is the total amount of time it takes to reach to its maximum height is equal to the amount of time it takes to get back on the ground. So the time it takes to get to position B is the same from A to B, is the same amount of time as it takes to go from position B to C. Or the time it takes to go from position A to position B is half of the time it takes to go from position A to position C. So these are some key concepts. And of course, once again, we're going to assume that there is no air resistance. If there was air resistance, these equations don't actually apply, because then the shape of the trajectory would not be symmetrical, and the time to reach the max height compared to the flight time are not necessarily the same, especially when you're launching things like golf balls, where the spin of the golf ball actually increases the amount of hang time because of something called the Magnus effect. But in any case, I digress. So our goal is to do two things. We're going to try to find the flight time and the range in terms of our initial velocity v, theta, and little g. And remember, little g is the magnitude of the acceleration due to gravity. Okay, so let's take a look at this, and we're going to talk about it from the perspective of kinematics, of course. So again, there's our three positions A, B, and C. Now, dya represents the position along the y-axis at position A. dyc is the position of the projectile along the y-axis at the end of the flight. Now, we know the acceleration due to gravity is negative 9.8 meters per second squared, or we're going to represent it in terms of g. So our acceleration due to gravity is equal to negative g. So the first thing we're going to do is, since we're looking for the flight time, or T subscript F, that is actually the time from position A to position C. So to do that, we have to figure out what our displacement in the y is. Now remember, in the kinematic formulas, dy is actually delta d, and ty is actually delta t. We just dropped the deltas because of basically laziness. So our displacement in the y is equal to our final position minus our initial position. So that will be our 0 meters minus 0, which of course is just 0 meters. Our vy1. Now our vy1 is the y component of the initial velocity. So our initial velocity is represented by just this vector v here. And of course we have the launch angle. So vy1 is equal to v sine theta. And that of course is up. And the reason why it's sine theta is because vy1 is the opposite of theta and v is the hypotenuse. While we're at it, to find the x component, we know that vx is adjacent to theta and v is still the hypotenuse. So our Vx is equal to V cos theta r. The Vx, of course, is going to be relevant when we talk about the range. But let's get back to the flight time. We're going to be focusing on the y component for the flight time. So we know the displacement in the y is 0 meters. Our Vy1 is going to be positive V sine theta. The positive implies up. Our V2y, we don't know what that is. That is unknown. And that would be the y component of the impact velocity. Now, of course, you could argue from symmetry, it should be just the negative of this, but we don't need to do that because we have enough information as is. Now, our acceleration in the y component, again, is negative 9.8, but I want to write it algebraically, so I'm going to represent it as negative g, because remember, g itself is just 9.8. It's just the magnitude. So the negative implies down. And of course, ty is our flight time, and that's what we are trying to find. So we're going to ignore the Vy2 because that doesn't help us in the situation. In any given problem, dy, or the displacement on the y, is given to be 0 meters. The Vy1 will be something that we'll be able to calculate based on the given information because we're assuming that we'll be given the magnitude of the launch velocity and the launch angle. And of course, acceleration due to gravity is a relative constant on the surface of the Earth, and it is assumed to be negative 9.8, but using it algebraically, negative g. Therefore, to solve this question, we are going to use the kinematics formula that does not involve Vy2, and that would be the following. dy is equal to Vy1t plus 1/2 ay ty squared. Now, normally we solve for time. I forgot to put my y there. We normally isolate algebraically for time, but since it's a quadratic here, we have our ty and our ty squared. We're going to substitute our values / variables in, and then approach it from that point and figure out what we can get for our flight time. Okay, so we know that the y component of the displacement is 0. Our Vy1 is positive V sine theta plus 1/2 bracket negative g times t flight squared. And I see a mistake already, so let me make that correction. Let's move that over, and we forgot the all-important tf there. Okay, so now there is actually already a solution to this problem, or at least one of them. And if you look carefully, there's actually one number right now that we could substitute in for our time that would make this statement true. And I'm going to highlight this. There we go, highlighting. If you think about it, there is one of two possible times where the height or the displacement in the y-axis is 0. And that is at the beginning and at the end. And at the beginning, the time that has elapsed is exactly 0. So if we were to substitute in 0 for tf, the statement would hold true because the entire right side of the equation would reduce to 0 and we'd get 0 equals 0. Well, that's awesome, but doesn't really help us with our problem. It simply just shows mathematically that we are in fact have two times in which the displacement on the y is equal to 0. But let's find the one that we actually want, which is the final time, the amount of time it takes to get to position C. So what I'm going to do next is I'm going to bring the 1/2 negative g tf squared term to the left-hand side, because this actually reduces down to 0 is equal to positive v sine theta tf minus 1/2 g tf squared. And since this is negative, when we bring it to the other side, this will become positive. So we get 1/2 g tf squared is equal to positive v sine theta tf. Technically, we don't really need to keep the positive here. So I think I'll just drop it at this point. Next, we can clean a few things up here. If you notice, we have a tf squared factor on the left-hand side and a tf factor on the right-hand side. So what we can do is we can divide both sides by tf. And what that does is it gets rid of the tf on this side and it gets rid of one of the tfs on this side. So we're then left with 1/2 g tf is equal to v sine theta. And now isolating for the flight time is a rather trivial affair. F is equal to 2 v sine theta over g. And this is our flight time. And remember, g is just 9.8. It's not negative 9.8. It's just 9.8. We already made it negative here. So the direction was here. Do not put negative in again, because then you're going to get a negative time, and that doesn't have any meaning. So it was already negative here. It's just when we brought it over to the other side, that negative turned into a positive. So again, G is just 9.8, no negative. Okay, so that's the formula for our flight time. Next, we need to figure out the range. Okay, so the range is the displacement along the x. And since we're assuming no air resistance, we can assume constant motion. So the dx is what we're looking for. Our vx, that is equal to our positive v cos theta. And our tx is actually equal to our flight time, which is equal to our new fancy pants formula, 2v sine theta over g. And again, since it's constant motion, we use the constant motion equation, which is dx is equal to vx times tx. So our dx is equal to, let's adjust the screen here a little bit, positive v cos theta times 2v sine theta all over g. Let's combine the numerators. First thing I'm going to do is I'm going to bring the two v's out front. Now, this is technically over 1. So the v cos theta is the numerator for our first factor. Well, we have v times v, that gives us v squared. Now, you might be saying, don't we normally put the number out front first? Just slow your roll, there's a reason. Yes, we could put the number 2 front first, but there's a reason why I'm not doing that. You'll see in a second. So we've got v times v, which is v squared. Then 2. Okay, it's still weird, I know. Then what I'm going to do is I'm going to put the other 2 terms in there because we have cos, then sine. But the order in which we do multiplication doesn't matter. So I'm going to write sine theta, cos theta, and that will be all over g. So some of you, hopefully, remember from math what this actually is. 2 sine theta, cos theta, that's your double angle formula. And that's right, folks, you can never get away from trig identities. And that is where 2 sine theta, cos theta is equal to sine 2 theta. So this gives us dx is equal to v squared sine 2 theta over g. And that is the formula to determine what the range is of a projectile that is launched at some angle on perfectly flat ground. This only works if the ground is level. Now, there is an optimal angle. There's an optimal angle for these types of questions. And it all has to do with this right here. Now, to maximize our dx, if v is unchanged, and of course, g we're assuming is a constant on Earth, the only thing that we can affect is our angle theta. Well, sine is at a maximum when the angle inside is 90 degrees. Actually, I'll put a little bracket in here. So this is maximized when equal to 90 degrees, because sine of 90 is equal to 1. Sine of any other angle is less than 1. Therefore, 2 theta equals 90 degrees. Theta must equal 45 degrees. So that is the optimum angle, which will give you the largest range. Let's test it out. Okay, so now let's start off with an angle of 25 degrees. So when we launch at an angle of 25 degrees, let's see what our range is. 25.3 meters. Okay, so now let's increase our angle to 30 degrees. And again, we've gone a little further. Let's zoom out a little bit here. Okay, so now we're at 28.6 meters. Let's raise it again, 35. And let's speed it up a bit. There we go. So we're at 31.0 meters, 40, and our range keeps on improving. 45, the optimal angle, and there we go. Theoretically speaking, it should now start migrating back again, so closer to our launch. So at 50 degrees, it should not go as far. And based on symmetry, it lands at the exact same point as when it was 40 degrees. Let's do 55, so on and so forth. And as we keep on increasing the angle, our range is getting lower and lower. But our flight time is getting longer because we're in the air longer. Oh, almost hit our target there. Okay, so I think we all see the point here. Incidentally, though, let's erase this. And let's talk about the 40 degrees versus the 50 degrees. Both will get you to the same point. However, when launching at a 50 degree angle, the flight time is a little bit longer and it lands with more vertical velocity. Whereas when we shot it at the 40 degree angle, it got there sooner. So if you want to arrive sooner, and let's say you don't have to go the maximum distance, the lower angle will get you there quicker. But if you're playing a sport like basketball, for example, it's actually better to have a higher arc because the projectile will have a more vertical component, which means the chances of actually going in the net is a little higher with the more oblique angle. If you launch it more horizontally like this, you're more likely to just bounce off the backboard. Physics and sports, man. Dig it. Okay, so in conclusion, the only time we can use these formulas are when we have to assume that it's flat ground, that there's no air resistance, that the value for g is just the magnitude of the acceleration, and the amount of time to reach our maximum height is half of the flight time. So next we're going to tackle on some of these sample problems. But before we do that, what I'd like to take some time is to describe the 5 different type of projectile motion problems that we're going to be dealing with. Now, this breakdown of 5 different categories is not a universally agreed upon standard. This is just one that I like to use to communicate to my particular students. So I break them up into the following. Type 1. These are the ones where projectiles are launched from the top of a cliff with no initial Y component. So they're horizontally launched. Type 2, you're launching from the top of a cliff as well, but at some angle. Now, in the first case, our Vy1 is 0 meters per second. But in our second case, our Vy1 is not 0 meters per second. When is it 0 meters per second? Here. At that point, our Vy equals 0 meters per second. But that's not at our initial. In both 1 and type 2, our displacement in the Y is negative because the projectile starts at some initial height and drops to some final height. And note, the displacement in the Y is just the difference in the height from the initial position to the height in the final position. It has nothing to do with what happens in between. So technically, based on my 2 diagrams, both cases would have the same displacement in the Y if they're both launched from the same height. Of course, in projectile type 2, our range is going to be a little bit bigger because we are actually launching it up, which means we increase the flight time a little bit. Our type 3, this is your flat ground type problem. And with the flat ground type problem, it is important to note that the height at the start and the height at the end is 0, which means that the displacement in the Y from the start to the finish is actually a total of 0. But in the middle, right here, that's where we reach our maximum height. So our maximum dy, our displacement in the Y, or our max height, and the time to reach that point is half of the flight time. And it's with these questions where we can use these fancy formulas that we just derived. Type 4 is kind of like the inverse of type 1. So with type 1, we launched it from the top of a cliff and it landed on the ground. Well, with type 4, we launch it from the ground to the top of a cliff. Type 4 is the most rare and it's the most difficult to achieve. Type 4 assumes that the projectile barely makes it to the top of the cliff. So this one would be very difficult to get in real life. So we're launching it at such an angle and such a speed so that when it reaches this point, it just stops rising and then it lands here. Now, of course, what would happen in real life is if our projectile landed on this cliff at this point here, let's try that again, it would continue to roll with its x component of speed. And assuming that there's no friction, it would just keep rolling at a constant speed along the x-axis. Of course, that's not real life. In real life, it would actually slow down, but you get the idea. Generally speaking, we don't assume type 4 unless we're told specifically that the projectile just barely made it to the very top of the cliff. Most times we're going to assume it's a type 5. And with a type 5 problem, that is basically, again, the opposite of the type 2. Type 2, we started from a cliff and launched it up at some angle and it landed on the ground, where the max height occurred somewhere during the flight. With our type 5 problem, we start from the ground. We land on the cliff, but it reaches its max height over here. So the Vy2 is not equal to 0 when it lands. The Vy2 is only 0 here at the vertex. Now that's useful information in some examples, but what we'd never assume is that the Vy2 when it lands here is 0. And again, the impulse often is to say, yeah, but it hit the ground, it stops. That's a different question. That's after it hits the ground, it stops. The Vy2 refers to the speed at which it is traveling just as it's about to crash into the ground. Also note, for the type 4 and type 5 problem, the displacement in the Y is positive. So as you can see, 4 and 5 are kind of like the negative of 1 and 2.